Good day, everyone. Let's start with something familiar. Have you ever noticed that a tightly closed jar lid becomes easier to open after dipping it in hot water? Or that the metal bridges you cross in summer have little gaps between their sections? These are all everyday signs of thermal expansion. When substances are heated, their particles vibrate more vigorously, pushing each other apart and increasing the size of the object. This effect is called thermal expansion. It depends on what the material is, how much its temperature rises, and its original size. So, in essence, heating boosts molecular motion, and that motion leads to expansion. Now let's classify this expansion. Depending on how dimensions change, there are three types: linear, aerial, and cubical. Linear expansion happens when only the length increases, like a metal rod, elongating when heated. Aerial expansion refers to an increase in surface area, such as a thin metal plate getting slightly wider. Cubical expansion is the increase in volume, like when a balloon swells as the air inside warms up. As you'll see in the diagram, the rod stretches in one direction, the plate expands across two dimensions, and the cube increases in all three. So, thermal expansion is simply expansion in 1, 2, or 3 dimensions depending on the shape of the body. Let's now focus on the simplest case, linear expansion. For a rod of original length L, when its temperature rises by delta T, the increase in length, called delta L, follows a direct law. Delta L equals L multiplied by alpha multiplied by delta T. Here, alpha is the coefficient of linear expansion with units per Kelvin. Each material has its own alpha value. For example, steel expands much less than aluminium for the same temperature rise. So, linear expansion is always proportional to the initial length and the rise in temperature. Next, let's move to 2- and 3-dimensional expansions. When the surface area A increases, the law is delta A equals A multiplied by beta multiplied by delta T. For a solid's volume expansion, we use delta Y equals V multiplied by gamma multiplied by delta T. Here, beta is the coefficient of aerial expansion, and gamma is the coefficient of cubical expansion. Interestingly, beta is roughly 2 times alpha, and gamma is roughly 3 times alpha. This shows a simple relation. Expansion in area and volume are just scaled versions of linear expansion. Thermal expansion is not just theory. It affects our daily lives in powerful ways. Railway engineers leave small gaps between tracks. Without them, tracks would bend and buckle in summer heat. Similarly, overhead electric wires sag more in hot weather because their length increases. Bimetallic strips in thermostats rely on two metals expanding at different rates, which causes bending and helps regulate temperature in appliances. Bridges are designed with expansion joints, so they can safely expand and contract with temperature changes. As you can see in the diagram, leaving gaps and joints prevents accidents caused by uncontrolled expansion. Let's solve a practical problem to see the numbers. Suppose we have a steel rod, length equals 2 meters. The coefficient of linear expansion, alpha, is 1.2 into 10 power minus 5 per Kelvin. The rod is heated through 100 degrees Celsius. How much will it expand? We start with the law, delta L equals L multiplied by alpha multiplied by delta T. Now substitute values. Delta L equals 2 multiplied by open bracket 1.2 into 10 power minus 5 close bracket multiplied by 100. That simplifies to delta L equals 2.4 into 10 power minus 3 meters, which is the same as 2.4 millimeters. Notice how even a few millimeters of expansion matters in real structures. Imagine hundreds of meters of railway track expanding. The effect can be huge. So, let's wrap this up. Thermal expansion is the increase in size of solids when they are heated. It can be linear, aerial, or cubical, and follows neat proportional laws with coefficients alpha, beta, and gamma. These coefficients vary by material, which is why different metals expand differently. In real life, engineers and scientists must account for expansion when building railways, bridges, electric lines, or even simple devices like thermostats. The expansions may seem small, but they are critically important for safety and design. So remember, heating makes molecules move faster, faster motion creates more space, and more space means expansion. I hope you now have a clear understanding of thermal expansion. In our next session, we'll look at another fascinating property of heat and its effects. See you then.